To bridge the gap between subquantum structures and the smooth geometry of our macroscopic world, we have to find a mathematical way to preserve information across two entirely different topologies. This is the Adelic Langlands framework, a vertical architecture designed to integrate global arithmetic with physical field dynamics. We'll build this framework from the bottom up, starting at the operator bedrock, feeding data through each tier to reach the global program at the top. This construction relies on a sequence of specific equations. By following them, we can prove that quantum fluctuations and geometric paths are actually two sides of the same data stream. We begin with the non-commutative Dirac operator. This operator acts on an infinite-dimensional Hilbert space, capturing the raw state of the quantum system. The problem is that raw quantum data is too volatile and divergent to be used in geometric equations. At this scale, the information is infinite and lacks a stable structure. To fix this, we apply a spectral projection measure. This acts as a mathematical sieve, using the projection-valued measure shown here to isolate specific, stable degrees of freedom. We achieve this by multiplying the operator by the Legendre UDD cutoff function, extracting a clean functional trace. Once the trace is calculated, the divergent quantum data is transformed into a finite trace class profile. This provides the stable foundation required for geometric optimization. Now that the data is filtered, we bridge it into the geometric engine of J-theory. This is the Grothendieck-Riemann-Mach push-forward. It maps the spectral density from our arithmetic variety down to the Hitchin base manifold, creating a smooth metric template. We then plug this template into the J-functional. By maximizing this functional, we minimize the critical points across the geometry, essentially smoothing out the topological wrinkles in the data. This optimization produces the semi-classical shadow of the original operator spectrum. We see this manifested as classical geodesic paths, the smooth trajectories that define our physical reality. To manage the global system, we use Logos field theory to split our field configurations into their constituent parts across the Adel ring. This factorization tensor reveals a sharp divide. On one side, we have discrete p-adic data packets. On the other, smooth, continuous fields. This transition involves a massive shift in information density. As we move toward the continuous boundary, the highly packed arithmetic strings decompress, fluidizing into a solid semi-classical volume. We cannot treat the boundary between these spaces as a hard stop. Doing so causes the local packing fractions to become unstable, leading to a breakdown in the global calculation. The solution is the Adelic-Tate-Mellon integration. This formula forces the infinite discrete factors from the p-adic side to dynamically interfere, yielding smooth gamma factors at the Archimedean boundary. This integration ensures that the rigid arithmetic of the quantum core seamlessly unwinds into the macroscopic field solutions we perceive as physical forces. To finalize the payload, we use the local Langlands correspondence. This ensures that the information contained in our spatial field flows is identical to the arithmetic data in our global representation. We return to the spectral trace expansion from our first step. In phase 2, this trace is reconstructed as a product of local Euler factors, effectively building the global state from local Dirac eigenvalues. This is the monodromy matrix. It tracks how the data stream is transformed as it circles a discriminant locus in the geometry, mapping topological holonomy directly to arithmetic shifts. The matrix factorizes into two parts, a continuous symplectic representation on the left and a discrete Weil-Deligne projection on the right. This exact matching ensures the information payload is preserved. Whether the system manifests as a discrete shift in a number string or a continuous path in space, the underlying data remains the same. The vertical bridge from subquantum operators to global arithmetic is now complete. This is the final Adelic Langlands functional equation. It balances the standard L function of the global field against its dual representation. We can now see how all four tiers interlock. The Legendre UDD filter, the J-flow, and the Adelic-Green's function all feed upward to satisfy this final global expression. This equation functions as a conservation law. It guarantees that the data decompressing from the discrete quantum core balances exactly with the smooth geometric energy dissipating into the macroscopic shadow. This functional identity confirms that microscopic arithmetic data and macroscopic geometric forces carry the same structural payload. The integration of the Adelic Langlands framework is complete.